So with this, let's switch to the keynote talk of the morning. Do you like to connect now? Yeah, just connect while I introduce you. So today we are very fortunate to have Professor Taisuke Boku from Japan, University of Tsukuba. He has been researching HPC system architecture, software, and performance evaluation on various scientific applications after he received his PhD in electrical engineering from Kyoto University. So he has been involved in deploying a lot of systems. Okay, I mean, he's very well known in this community, but if you don't know him, he has been from University of Tsukuba and also from Japan. He has been involved in the Exascale project, really deploying very large-scale systems. And so he has been, he is currently the director of the Center of Computational Sciences, a co-designing center with both application researchers and HPC system researchers. He has been playing a central role in the development of the CP packs, that is the top 500 in the 1996, and then a lot of other systems. And today we'll be talking about a new system they are trying to deploy. But one interesting thing I want to say, I remember we have been working on MUG'22 for many years. I think cluster was when 2008. 2008. Yes, T2K. Yes. So they were using MUG'22, and cluster was there, and it was not running. It was MUG'22 was crashing. Okay. So I took one of the students that time, Matt Coop. If some of you know, he is now a director at AWS. We went there and sat through the night. Okay. You run HPL and it just crashes. Okay. I think it took 12 hours really to debug what was happening on that system, and finally things worked. Okay, so we are able to really provide, I can say, on-site support, international manner on that system. But that's how these systems work. I think those of you know how the new systems come up. We are always not only leading technologies, but people call bleeding technologies. Am I right? We have been working. So it was very nice to go that time and see Professor Boku's universities, labs, supercomputing centers, and all. So with this, let me hand it over to Professor Boku. Today he will be talking about Cygnus BD, the big memory supercomputer for HPC, big data, and AI. So let's give a hearty welcome to him.
Hello, good morning, good afternoon, or good evening, everyone. My name is Taisuke Boku from University of Tsukuba, and I'm currently the director of our center, named the Center for Computational Sciences, University of Tsukuba. So first of all, I'd like to thank very much to DK Panda that he kindly invited me here as a keynote. Actually, in these years, every year he asks me to, why not come to the Ohio and Columbus, and unfortunately, I had not a good chance so far, but this year, finally, I came here. So I must confess that coming here, I have almost no knowledge about Columbus and Ohio State. I'm very sorry. But yesterday, DK kindly arranged some short excursion of the OSU. So I was really impressed at how this OSU University is doing a lot of things and have a really wide campus, and also mostly impressed in all other research direction is older state of the art, and so that I really admire this university's research activity. So you OSU people, students, you have a very good environment, and I believe that this is one of the top levels universities in the United States and the world. So before talking about our system, I have one joke. Yes, that only the knowledge about the Columbus city just came from a movie named Ready Player One. Do you know the one? That is directed by Steven Spielberg. And it is a virtual reality movie. So it's a really fun movie. So if you have a chance, please look at it. So that is a future Columbus city. But unfortunately, it is totally different from this beautiful Columbus. It's actually a sort of that city. It's a very, very fun movie. Okay, so let's move to today's my talk. But before my talk, I want to talk very briefly, maybe 5 minutes, about the next step of the Japanese national flagship system, if you're interested into that. It is absolutely not related to the MPI, but this is a brand new and latest information about the next national project of Japan. The content is, don't expect anything. The content, nothing is decided yet, but I want to show there some framework of how we proceed on the next 80 years towards the next system. Is it okay? So I want to switch my slide here. Can you see it? Okay, so it's titled the Feasibility Study on the Next Generation Flagship Supercomputer in Japan. So this is actually the step 0 towards the post-Fugaku system. Of course, with several tens exaflops or exascale system. That is our goal. And I'm the director of our center university, but also I'm the program director of the next gen computer platform research project. So as the step 0 towards the post-Fugaku system. So there are actually 3 PDs in this program, and I'm one of them, most likely working for the research on the hardware system. Oh, does it work? Oh, okay, it works. So this is a past that, the Fugaku system is now the number 2 system in the world. So it got the number 1 position with about 430 petaflops. And it is, unfortunately, didn't reach to the exaflops. And after that, the United States Oak Ridge Frontier system finally got the number 1 in the last June. And maybe it will continue in the next November because the other 2 exaflop system in United States will be a little bit late. But anyway, so the Fugaku machine is a completely pure general purpose CPU based system with about 150,000 of the computation nodes. So each computation node provides 3 teraflops of the general purpose performance based on the 1 terabyte per second of the HBM2 memory. So the machine is really easy to use. So actually, one of the big purpose of the construction of the Fugaku system is they want to make a pure continuation from the K computer. K computer is a 10 petaflops, only 10 petaflops machine these days. And it's aimed to 1 exaflops, but maybe basically the problem of the budget. So finally, it makes about a half exaflops, so 500 petaflops peak, or 430 petaflops on impact. So anyway, Fujitsu made this system, and the Riken RCCS is now operating that one. And during the design and the construction of the Fugaku system, I was also a member of the working group of the hardware system. So I know everything inside about Fugaku, but today's talk is not on Fugaku. So after the Fugaku got the number 1, as I told you, so many accelerated supercomputer system is still ongoing in the United States, and especially the Frontier system by Oak Ridge finally reached to the 1 exaflops impact. And maybe you know some knowledge about also Chinese machine. It is really mysterious and secret systems because there is no evidence that machine is actually running, even with that impact. Only evidence is a Golden Bell Prize approach. So I'm also one of the member of the Golden Bell Prize committee from last year, so I know the inside, but I cannot tell as others. So what's the next step in Japan? So following to the flagship system Fugaku, and it started, the next gen plan started last year. And for the first 2 years, we will use these years, this year and the next year for the so-called feasibility study, or FS for short, before basic design for the next generation flagship system. So possibility of 1 year extension is now under discussion. So target year and performance. The most important, and everyone wants to know that what is the next flagship machine's target performance? No one knows, because our current machine, including the US system and the other countries one, is all reaching to almost 1 exaflops. So that if we make this machine 2030, no one will be satisfied with 10 exaflops. That's easily fine. But then, is it really possible to make over 10 exaflops or 50 exaflops or 100 exaflops with only 80 years later technology? That is a big, big question. So at this moment, Japanese government and we didn't make any goal of the performance of the next generation so-called post-Fugaku system. So instead of that, we will run the 2 year of the feasibility study FS program in the 2022 and 2023 or fiscal year until maybe the 1 year extension with some gating at most 2024. Then the end of, sorry, not EOF, EOL. I'm the system guy, so I like the word of the EOF. Sorry, EOL. So end of life of the Fugaku is currently planned as maybe 2028 or 2029 after the 8 to 9 year of the running period. So roughly, we are thinking perhaps, oops, doesn't work? Well, perhaps the next machine will come around 2030. I cannot guarantee anything. No one can guarantee that, but roughly 2030. And the purpose of the feasibility study is that we are thinking that the CPU structure, of course, and most importantly, there is a big possibility to introduce the accelerator. I don't say that it is a GPU, but some kind of accelerator must be used in this generation, I think. So Japan has, as a national flagship project, Japan has a big behind to the United States. The United States already moved to the older GPU-ready system, but Japan is still running the pure general purpose CPU system. But finally, this is the time to introduce the accelerator. I strongly believe that. And of course, interconnection and a new generation of the technology, like quantum computing. So no one believes that 2030 pure quantum computation is an overall so-called HPC supercomputer. I think, I don't believe that. So one of the topics is that how to combine the QC technology with the traditional HPC technology like a supercomputer, silicon supercomputer, and so on. That is a very, very interesting and important issue. So also the system software, of course, OS and runtime and library, and most importantly, applications. So what kind of application can survive on this era? Of course, there are a lot of limitations of the power consumption and the sustained performance or floating point formation and so on. So we must carefully tune the application and keep that what is a killer application or what is the killed application. Okay. So conclusion of the FS is just we roughly design the system. So there are 4 teams I will show later. And each team must prepare, propose some kind of the rough sketch of the system and the rough, the goal, and also the budget and the power consumption. But, and after that, next, Ministry of Education will evaluate that all these results and make a choice of their system. So target performance, no one knows that. It's still unknown. Okay, so I will quickly show that. So yesterday, last night, I made some translation from Japanese to English. So all the Ministry of Education's resources just in Japanese. So I made this one at first time. So please forgive me that there is still the remainder of some garbages here, but this information is not so important. So there is a Ministry of Education side construction or formation of the program directors. I'm the one of the program directors team out of 3. And also there is a steering committee. So steering committee is the combination of the program directors and each program leader or PI of 4 systems. So we had 1.5 months of the call for proposal, and finally 4 teams are selected as a feasibility study. So first, the biggest one or maybe this is a central one, is led by the RIKEN. And they research on the architecture and system software and applications, everything. And most of, roughly counting, 80% of the HPC central researchers in Japan are involved into this team. So like most of the universities and also several companies like Fujitsu, AMD, and Intel. And Jamstack is an old Earth simulator holder. And National Institute for the Material Science and other universities. So, of course, University of Tsukuba, my center, is involved in this one. And second one is a completely different style of the approach. It is mainly focusing on the low power technology. So the central part is taken by the preferred network. This is the name of the company. So PFN. PFN once got #1 in the Green 500 with their very excellent low power technology before their frontier came with MI200 AMD GPU. So they are very professional about how to save the power to keeping the performance. So still they are top 3 of the Green 500. And there's a leader from Kobe University. So they also work all the layers like architecture, system software, and applications. But total formation of the team is much smaller than the RIKEN one. So RIKEN is the biggest one, and they have the largest budget actually assigned from the feasibility study. Next two are something different. So the new fundamental technology led by the Keio University, it is quantum computation. So as I told you, they don't think that the quantum computation is the main part of the next-gen flagship machine, post-Fugaku. But we need to carefully design the interface and the programming structure of how to use QC as a part of the really complicated application or simulation, which is mainly run on the next-gen supercomputer, but sometimes it calls or offloads some function to the quantum computation. So that is their research goal. And finally, the operation environment. This is a very, very traditional work, is how to control the temperature or operating system management, and also the user job scheduling and so on. So this is maybe the most concrete part led by University of Tokyo. So these 4 teams have a sort of the competition to make a proposal of their next-gen supercomputer. So their feasibility study research will end on the March 2024. And there is some gating. Perhaps they will extend 1 more year for the more detailed feasibility study. And finally, this is a Ministry of Education. By the way, MEX means the Ministry of Education, Sports, Culture, Science, and Technology. So everything about the academic research. So it is too long, so we just shrink all these words as X. So it's called the MEX. So the evaluation team committee is actually is a very high level, and they are almost just wait for the research result. And mainly, the project is led or directed and or supervised by the this project's program directors. So there are 3 PDs, Professor Kobayashi from Tohoku University, and Professor Taro from University of Tokyo, and me from University of Tsukuba. That's the formation. Okay, so this is my last slide. So this is just my personal summary. I cannot guarantee anything, and MEX guarantees nothing here. But we are around 1.5 year of the feasibility study, or maybe too short. So there are perhaps 1 year extension. And the target year of the system completion is also not fixed, but we roughly think that 2030, running the April 2030 is one of the current target of the starting of the operation. No, I don't guarantee, okay? So this is not the public information, just in our mind. And there is a summary of what is focused on all 4 teams. So system research 1 by RIKEN, this is the largest part and mainly all of the traditional HPC system construction, but also they focus on the, especially for accelerator. I will guide their discussion with how to introduce and what kind of accelerator they propose. And second system research tool is a preferred network, PFN, gives some low power technology. And new fundamental technology of the QC, quantum computation, we need some interface and how to utilize that QC beside of the traditional HPC system. And finally, operational environment is very concrete one. So that's my information today. I can talk. Okay? If you have any question, I will be happy to answer, but maybe there is no answer. Okay, so please let me go into my main topic. So we are now planning to introduce just the next 2 months of our brand new system. And this is maybe one of the world first runner of the couple of the latest technology combination. And we tentatively named the machine as Cygnus BD. So Cygnus is our currently running supercomputer name. Oops, it doesn't work again. Sorry. Oh. Okay, never mind. So BD means big data. So we call this one as a big memory supercomputer. So and the big memory, hint of the big memory is persistent memory or NVLA, non-volatile memory, RAM memory. So many people know about Intel's current the plan is something crashed in the near future, but I will explain about the situation later. Maybe the final slide. So this is our new machine, just going on to introduce in our center as a new machine, Center for Computational Sciences. And also there's a very strong, my co-worker, Professor Osamu Tatebe here. And he's actually the leader of the, excuse me, I will use PowerPoint pointer. So he's a leader of the order procurement and management and the design of our supercomputer. So 3 years ago, I was playing that role. Then I was assigned to the director, and now Tatebe-san is working on that part. And in the research part, mainly that is his work. So at first, I'd like to briefly introduce our center. So our center is named CCS for short, Center for Computational Sciences. And it's established in the 1992. So this year, we successfully celebrate the 30th anniversary. And in the next October, we will have our 30th anniversary symposium. Maybe I will introduce it at the very late part. So after 12 years, the running named under the name of the Center for Computational Science, Physics, then we organize and expand the target applications into all kinds of science. So now it's run as a Center for Computational Sciences. So we have 45 faculty staffs from the assistant professor to the full professor. And also we have 8 research divisions. 6 of them are applications like quantum physics and astrophysics, or material science and nuclear science, and climate and bioscience. And the other 2 are on the system side, and HPC system, and also the big data and informatics. So I'm also the leader of the HPC Development Research Division. And so it is a very, very ideal structure of the center, because from the scratch, 30 years ago, we already started the so-called co-designing. So this is a pure co-design center because we have both the application side and the system side researchers, about a 2-to-1 ratio. So I think this is very ideal. And this is one of the National Supercomputer Center on the next. It means that we have a lot of users, about 300 to 400 users every year to accept their approach for any research advanced research on the computational science. So this chart shows the history of our center. So before our center established in the 1992, University of Tsukuba actually started very basic parallel processing research from 1978, more than 40 years ago. So that machine is really small, only 9 nodes. Each node is equipped with the Motorola 6800 8-bit microprocessor without any floating point acceleration, just a pure 8-bit microprocessor. That is the start of the history. And we developed a couple of machines, but in the middle part, 1996, we finally made the CPPAX machine that was ranked as a #1 in top 500 list, is the November version of the 1996. Then other machines. So there is no picture of the T2K Tsukuba system, because T2K Tsukuba system is not a project machine. It is a production machine by the governmental money. So we didn't include the T2K machine here, but the T2K machine is very important between our relationship with me and the DK, because so he was so interested into the 4-layer InfiniBand solution. I think that there is no other 4-layer InfiniBand ready solution in the world, so he wanted to make a challenge to import the MBAPitch MBAPitch library into the 4-layer InfiniBand. It is successfully run. And we continue to run the 4-layer system after the T2K, and in the next 3 generation of the accelerated supercomputer. So currently we are running the latest machine Cygnus, which is installed about 3 years ago. But today's my talk is the next one. So as I told you again, we are a pure co-design center, and we have application and we have system-side technology. So this is a very good coupling of the seasoned needs of the proceeding the computational science and the computer science. So Hpc technology contributing to the AI. So the key issue of the next machine is how to combine the HPC and the AI. So as you know, that so far, many of the HPC technology, like the CPU and especially GPU interconnection, or maybe recently the DPU or some other HPC latest technology contributed to their AI. So that AI is driven by their so far HPC technology so far. And even their CNN or deep learning is on today's main AI application, and that is supported by the older HPC technology, and especially GPU accelerator. So now the NVIDIA is totally focused on their AI business, while the AMD is between imbalance of the HPC application and the AI application. That is a very interesting balance. But anyway, so NVIDIA and the AMD, followed by Intel too. I'm not sure that when the actual Ponte Vecchio will finally come to this world, but it's a delay and a delay and a delay, as you know, from the original 2018. But anyway, so that GPU is currently the most important module in supporting both the HPC and the AI. And the CPU instruction set is also changed. Even the Intel Xeon processor, now to support the machine learning, there's a FP16 or a FP8 or bfloat16 and other very short lengths of the wide vector calculation to support the AI. So on the other hand, how the AI contribute to the HPC? So recently many approaches to use the AI technology to make a good acceleration of the HPC. So for example, machine learning for the data screening or targeting the some specific parameters to focus on each large-scale HPC simulations is led by the AI. So you know that there is no time to run older combination of the parameters. So AI strongly helps us to find the way of the correct way to how to shrink the parameter search space. That is a big advantage of using the AI for the HPC. And there are many of such an application, even the climate simulation or astrophysics or life science. And data matching on the large data space is also important for the big data solution. And another important science is the so-called data science. So analyze the data and getting the new knowledge and the phenomena, find out new phenomena. That is a current trend of the data science. And also recently, surrogate modeling is focused. But I'm a little bit doubtful about the surrogate modeling. There is some limitation which is applicable with surrogate modeling, or just we avoid the pure computation and makes a wrong result. So surrogate model is very interesting and today's focus, but not perfect. So our goal is that how to make a good combination of the HPC for AI and the AI for HPC together. So they must work as a two wheel of the driving car, as application and system are also two wheels of the car. So storage technology, we focus on the storage technologies here. So maybe someone knows that, but today is one of the bottleneck of the really big size of the AI processing or data science is bottlenecked by the memory capacity. So today we are mostly running on the DDR-based system and or some other advanced processor using the HBM2 technology. And of course, GPU are all accelerated by the HBM2. But there is not enough size. So one of the weakness of the HBM technology is always how we are implemented. We cannot extend the size of the memory, even we have money. Okay, so that the last solution is just to divide and conquer the problem into the small pieces. And in that case, the communication, of course, the MPI is running very well there, but then even with the fast MPI like MPitch, there is some communication overhead. So what we are today doing is that pays much of the communication overhead just to increase the total memory size. And it doesn't scale in some days because next slide, I will show that actually the memory size is not fixed. It's shrinking in the comparison with CPU performance. So data science driven by the large capacity memory and the high-speed shared storage is a really big key issue here. So we think that we solve these two problems, memory capacity and the fast data sharing with a really fast ad hoc file system can be solved by the new technology, persistent memory or NVRAM, non-volatile RAM. That is a key idea of how it makes a Cygnus BD system. So this chart shows that comparison between the increase of the performance and the decrease of the memory capacity per core. So you can clearly see that the performance is increased in there about 2 digits higher for the processor. On the other hand, the memory capacity per core is reducing. So far, many of the Linux systems has about 2 gigabytes per core. That is almost enough in any size. But these days, the latest one has only 0.64 gigabytes per core in the Tsukuba system because it has 48 cores, while the memory capacity is only 32 gigabytes, limited by the HBM2. So to support the big data and the large data computation, both for the HPC traditional simulation and also AI calculation, we think that the persistent memory or NVRAM is the next key issue. So this is an image of where is the PMEM or a persistent memory. From now, I call the PMEM or NVRAM, maybe PMEM as the NVRAM technology. So the horizontal line shows latency and the vertical line shows bandwidth. So there's almost, of course, you are a computer scientist, so you know that there is no perfect solution with large capacity and high speed memory. So we must choose the capacity or bandwidth. And PMEM is actually located in between the SSD technology and the DRAM over there. So that is a new one. And so the goodness of the PMEM is especially Intel Optane product that is based on the 3D crosspoint technology, that we can utilize that memory module in 2 ways. One is an addressable block, such as a very fast SSD. The other one is byte addressable memory. So this is just a pure extension in the same address space with the DRAM. Or we can use the DRAM as the fourth level cache of the PMEM. That is also possible. So there, we already very well to working the how to shrink the current working set because we have a good technology to run the cache system in the current CPU. So in that meaning, PMEM is maybe directly accessed with for the just a really wide 2 terabyte up to 2 terabyte of the memory space, or using the DDR as a cache of the PMEM. So both ways. So in the Intel terminology, memory mode means byte addressable memory, and up direct mode means sort of the I/O system with a block device. And consideration of the future of the persistent memory. So maybe you want to say that there is no future on the persistent memory because Intel announced that they will stop the production before 2025. But I will mention later about that. So, but anyway, PMEM is a really good device. So Intel explained us that it's a really good device. Only problem is that the commercial market, there are not so many users. Maybe this is a little bit too early technology to while everyone cannot catch up how to utilize that one, especially for the data center. So data center is still working on their PMEM solution, but HPC people are much more interested into that. So that so currently the PMEM is about 10 times more cost effective, and also 6.54 times less power consumption. So not just the price, not just the capacity, also the capacity per watt is reduced very strongly by the PMEM compared with the DDR. That is another issue because memory power consumption nowadays is very, very serious, as well as the CPU and GPU. Of course, the CPU and the GPU are also very increasing the power consumption, but the memory power consumption is another bottleneck to make the real system, not just the money and the number of slots of the DDR. So this device technology evolves with CXL, Compute Express Link. That is on some sort of the extension after the PCI Express Gen 5. And in that CXL technology, we can guarantee the cache coherence between the PCI Express device and the CPU memory. So the new installation of using the CXL of this memory system is that we have a very big memory based on the same technology with the PMEM, not the 3D cross point, but NVRAM installed in the PCI card. It's inserted the slot with the CXL, then byte addressable, and also the cache coherent. That is a new solution. The Intel is shifting from the ordinary 3D cross-point technology to the CXL-based technology. That is today's story. So anyway, and the research and these industry activities are still increasing, and there are many papers every year issued. You have a question? Okay.
So regarding the cost effectiveness measure that is used to judge the persistent memory cost effectiveness. So in practice, we noticed that persistent memory has also 10x loss in bandwidth compared to DRAM. So if you run the traditional stream benchmark, if you go beyond the L4 cache, that is the DRAM, you start degrading the bandwidth, and it ends up being 20 gigabytes per second. So that's maybe 10x loss in performance. So how is that cost effective considering just the memory bandwidth?
Okay, so a very good question. So that there are two answers. First one is I already told that, as I already told, that the one idea is using the DDR as a cache of the PMEM. So we are already familiar to how to use the cache with the DDR. Then it shifted one level down to the DRAM and the PMEM to controlling carefully about working set to keep on the DDR. That is automatically working. The second answer is that even the bandwidth is a little bit lower than the DDR, the capacity is very big, and that latency is much higher, much shorter than the communication over the InfiniBand. So as I told in the beginning, so we are now paying the big communication overhead just to increase the memory capacity. So that is, the PMM solution is much better to pay their communication costs. So that we think that it works. Of course, it is still ongoing technology, but we like to prove that. Okay.
Thank you.
So there, okay, so that is a chart of the number of papers, and Taisuke-san give me the chart. Okay, so there, I'd like to briefly introduce a couple of, we are focusing on the applications. One is astrophysics. This is not a simulation. This is a telescope analysis. So every day, a lot of telescope data from the universe will come, not just the very recent the telescope in space, but even on the Earth telescope like the Subaru in the Mauna Kea of the Hawaii Island. Every day, tons of the data is coming, and we need to process everything with some combination of the frame task and the FFT and so on to get a good result. So currently, they are lack of the memory capacity, and they need more size of the capacity of memory up to at least 10 times larger. So they're running 128 gigabytes or 256 gigabyte memory system, but our new PMM supports 2 terabytes of the memory capacity. So there is almost no need for the communication. That is one of the example. The second one is genomic data accumulation. That's led by our bioscience team. And they also have some sequence data and the processing. This is very similar to the telescope story, that genome sequencer makes a lot of data, and we must make carefully filtering and also pattern matching. And that they must run the large-scale parallel processing for the human genome and other genome analysis. And can work even both for the large capacity memory. And also later, I will show our latest technology to make PMM, using the PMM to make ad hoc really fast and short access time shared storage. So there are both the shared storage solution and the large capacity memory solution works for this application. The third one is a very simple, straightforward calculation of the climate simulation. So we have a very good simulation code based on the large AD simulation, or LES, in the city size 10 kilometer over 10 kilometer by 2 kilometer height of the model. It's really detailed because every grid is just 1 meter size, and very detailed. And we successfully ran the GPU version of this one. That's about 10 times faster than the CPU version of the Xeon. Yeah, but still, their memory capacity is a problem. So we are reaching to the crossover of the communication overhead and the computation overhead. So in some certain size of the system and the certain speed of the computation, so it's reversed. So communication overhead is really serious here, and we are now making the PMM version of this simulation. And finally, this is a little bit different story, but one of our section of the big data science is working with IIIS in University of Tsukuba. IIIS stands for the International Institute for, what is the third I? Sorry, I'm not directly related to that organization, but the last one, S, is the sleeping. So now the human sleeping is one of the very important, application for the human health care. And the government pays some money for the research on the sleeping. And the analysis of the sleeping so far is that we must have a very heavy headgear. If I put this one, maybe I cannot sleep. But anyway, so that they analyze the wave of the human brain by a lot of sensors. And finally, doctor judge what is the status of his sleeping at this moment. But we introduced the AI technology for the very good analysis, and also the very small and small number of the sensors which I can sleep even wearing that gear. And the result is very, very close to the expertise analysis. And so the upper one is expertise doctor's analysis, and the lower one is AI analysis. And there are several stages of the sleeping, from the waking and so-called REM sleeping and the deep sleeping, so that it's almost perfectly matching. So that our university launches a new company for their to sell that's the solution for their sleeping healthcare. Okay, I have 15 more minutes. So that these couple of slides, I just straightforwardly explain about how the large capacity memory supports many of the science. But here, I'm discussing with some professor of the molecular dynamics to make the next generation of the MD simulation. Of course, it is really gigantic. And the parameter search or space finding is the most important job. So they are writing to introducing the AI for the shrinking the parameter search space and makes a big computation on the Fugak system and other supercomputers. So here, the AI and the HPC are directly coupled. And this is sort of the ecosystem together. And this is, his name is Professor Okuno from Kyoto University. And his model is something like that. So the screening or a neural network, deep learning search makes some set of the parameters to find. This is biomolecular science. So the parameter is not just a single number. It still have a lot of models and very complicated models parameters. But it is almost impossible to find out by the human hand. But AI strongly supports this one. So this is one of our goal to HPC for AI and AI for HPC. So finally, okay, so I will introduce our next system. So so far I explained the PMEM, and we, in the last 2 years, we are researching how to use PMEM for the many other applications. So the first one is the ultra-large capacity of the memory, like a climate simulation. Second one is the so-called in situ processing. So in situ is, both processing and the analysis together. But of course, easily understand that memory capacity is a problem. So PMEM will be one of the good solutions. It is much better than storing the data once to the file system and retrieve them after for the follow-up process. And a high-speed distributed storage system. So last part I will explain a little bit later. So this is current our system named Cygnus. So Cygnus is a completely different style, extreme scale computing system supported by the two kinds of accelerators, GPU and FPGA. So today, this is not my main topic, and I will briefly skip this one. But we are running the 18-node system, but each node is very heavy with 4 of the NVIDIA Volta V100 GPU and 2 of the Intel Stratix 10 very latest FPGA. So the coupling the GPU and FPGA is a really interesting story. I like to talk about that, but today I will skip this scenario. But this is a schematic chart of the one node. So it is really gorgeous and heavy nodes with 2 Xeon CPU Gold and also the 4 NVIDIA GPU V100 and 2 FPGA Stratix 10 by Intel, and also, as usual, in our center, 4 channel of the HCA InfiniBand 100 EDR. So we use, of course, MPitch here. And MPitch 2 is only one officially support MPI here, Cygnus. So nowadays, we can introduce MPitch 2 without any help of DK's team. If we find any problem, I will ask you. So, but then on the next system, of course, we coupling the GPU and the PMEM, and also the multi-layer. This one is not multi-layer because node is a very thin model. And okay, so I will skip this one. How the GPU plus FPGA combination is really working. If I have time in the coffee break, I will talk about that. So this is actually the complicated simulation model with multiple phenomena. So for the multiple phenomena, our answer is that we need to introduce multiple accelerators. But about the big memory supercomputer. So our next challenge is how to combine the GPU technology and the AI for HPC and HP for AI based on the PMEM, large capacity memory, and also large capacity PMEM supports both the direct memory mode and also the I/O with a very fast, much faster than the DDR's fast cache system. So we designed a big memory supercomputer, which will come in the next two months. Well, okay, so this is the first, really first chance to announce our new machine's name officially. So far, we named it the Cygnus BD, BD for big data, but finally we decided to put a name with Pegasus. So Pegasus is another constellation beside of the Cygnus. So imagination, one day when I fly over the Tsukuba to Kobe on the flight, I just watching the wind. So wind is very big, and that make an inspiration for me that a big memory is something like a big wing of the airplane, and the big wing is one of the animals. Of course, on the imagination is a Pegasus. So we decided to put the name of Pegasus on the Cygnus BD system. So the Cygnus system is for the extreme computing, and the Pegasus is for the big data. So far, you know, the BDEC, big data and extremely computing is a catch of the combination of the both sides. So this is a constellation Pegasus with a very big wing and very fast running. So that is our new model. And just coincidentally, I found that the chart of the space and the Cygnus and Pegasus is actually side by side. So they are sort of the brother or sister machines. So that is also a big reason why I named this machine as a Pegasus. So this is a block diagram of the Pegasus node, which will come the end of the October. Yesterday, I had a very bad news that perhaps there is some delay of the delivery of any module of the Sapphire Rapids or PMEM obtained still. But that always, is there anyone from Intel here? That's always from Intel, okay? So that I've never seen that the delivery is on catch on schedule. So I'm not so surprised, but it is a brand new combination. So I told you that this is a really brand new system because we introduced NVIDIA H100 as the first large cluster in Japan, also with Sapphire Rapid. So Intel still didn't allow us to tell the detailed data performance of the Sapphire Rapid, but it is some sort of the couple teraflops. Now it's almost reaching or overcome the Fugaku's processor's performance. Now we have only 128 gigabyte of the DRAM, but plus 2 terabyte of the PMEM. You know that the Optane is actually combined with the DDR part and the PMEM part to easily install on each ordinary DDR slot. So it was automatically configured with some capacity of the DDR plus PMEM. And also we have NVMe SSD as usual of the local storage with 64 terabyte. And we have totally 120 nodes. It is not so gigantic system. And each node is very thin compared with the Cygnus system. Cygnus is a fast system with 4 GPU plus 2 FPGA and 4-channel InfiniBand. On the other hand, we introduced a brand new NVIDIA Mellanox InfiniBand with 200 Gbps. As Gerard knows that, this one. So anyway, we ran about roughly 6 petaflops of the peak performance system. So still, NVIDIA didn't tell me that what is the estimation of the DIMPAC or DGEN on the H100. We are still no chance to test the real H100. So we are waiting for the NVIDIA's results. But anyway, this is a very fast system with H100 ready GPU cluster, not just as a PMEM. So we introduced everything as a brand new module. You know, the combination of the brand new modules no one can guarantee that it's stably running. So that is our next challenge. And NVIDIA's quantum to InfiniBand with NDR200 is installed, both for the switch and the HCA, of course. And finally, we have a not so big 7.1 petabyte of the DDN file storage, because we don't need that fast cache, because we have our original file cache system based on the PMEM. So this is just a comparison. I will provide the slide later, so you don't need to memo this one. So there is no FPGA. So this is focusing on the PMEM and the GPU only. But Cygnus, or the Cygnus system is a combination of the GPU plus FPGA. And the system is continuously installed by the NEC. The Cygnus is installed by the NEC and the Pegasus too. Okay, so the last minutes, I will give them a brief shortcut for the research on the new file system named CHFS. That is a work by the Professor Tatebe. And simply, we introduce no metadata, flat, and also the hash table file system for the ad hoc file system. So the point is that this is not a permanent file system. Maybe the permanent file system requires any of the metadata construction. But this is an ad hoc file. Ad hoc means that when the job runs on the multiple nodes, the file system is constructed there. And after all the processing, it's gone. So, but the ad hoc system, a file system works very well for also the intermediate analysis of the many of the applications. We found that. So we make a distributed file system with only the running node, not outside the other jobs node. So this is ad hoc. And CHFS, that stands for Consistent Hash File System. That is a new one designed by Tatebe-san. And it currently have a very good performance with a small PMEM system and also a large SSD-based system. And I'm sorry, I will skip these parts. And if you're interested into the CHFS technology, please refer the last January's Hpc Asia 2022 paper. There is an accepted one and published from the ACM. Okay, so the file system design is something like that. We just use key value store technology. So PMEM KV is an open source version of the key value store on the PMEM hash system, PMEM system provided by Intel. And we perfectly use that one, and it works very well. And to make just a pass is a key, and the contents, including the metadata, is a value. So there is no metadata server. Always a big memory, big file system, metadata server is a big serious bottleneck. So we remove that completely. And design features here, and also, I'm sorry, but I will skip this part, just the characters. So and this is a schematic image of how to make CHFS as an ad hoc file system on the PMEM system. And finally, it's implemented already with based on the couple of other underlying technology, like Mochi or Mercury and Argobots by the Argon and so on, and PMEM KV by Intel. Finally, I would like to show briefly the performance result. We have some 4-node extension equipped by the Optane 2, additionally in the Cygnus system, to support, to have a development of the CHFS. So here you can see that the leftmost bar with a purple color is the CHFS, and all others are some other competitive different kind of the file system. So we see that this is the vertical bar is the bandwidth, so the higher is better. So that we can see that all three of them, so the CHFS is number one. And when we increase the number of the, what's happened here? Anyway, so they're increasing the different type of the I/O bandwidth test. So always increasing the number of nodes, always CHFS is almost the best, except the IOR ER. And the scalability of the CHFS up to 4 nodes is very good compared with other technologies are something bottleneck. And that is, again, so on for the metadata easy. So actually, there is no metadata on the CHFS. So of course, it is much faster than other metadata-based system. Okay, so that's all I have today. And for the conclusion, we are currently ready to introduce almost the last phase of the old Cygnus BD system, currently named Pegasus. And the CHFS development on the PMM is doing well. We will put some new data perhaps in the next November version of the I/O benchmark. And covering the large capacity memory and high performance shared file system, both together. PMM can be split into the some combination of the addressable mode and also the storage mode. So we find the good combination. Finally, about the latest news, just 2 weeks ago, Intel suddenly announced that they will cut the production of the Optane to 2025. So we really lost our way. But we have a couple of very detailed meetings with Intel and NEC and Supermicro, which is a provider of the motherboard. And our goal is that we are ongoing to introduce, because we already contracted to introduce the system. And this is not the complete shutdown of the production. They stopped the production at 3 years later. And after that, they have a 5-year warranty of all support on the hardware and software. So that is enough for our lifetime of the supercomputer. We are assuming about 5 years. And I guaranteed that some special early access to the OSU people to test MBPitch here. So you can test the first H100 and the PMM combination with NVIDIA's or Mellanox NDR200.
Thank you.
So please wait for that. Okay, so that is the story, MBPitch to test on the Pegasus. Okay, this is the end, and it just summarizes all I talked today. So thank you very much for your attention.
We'll have some questions. I think we'll have. Please use.
So would this new Pegasus system support like network offload or the DPU technologies from NVIDIA, like Sharp?
Sorry, it's a little bit echoing and difficult to read.
Would this new Pegasus system support the network offload capabilities like Sharp as well as the DPU technologies?
No, just purely the InfiniBand, traditional InfiniBand with 200 kbps.
Thanks.
Yes. I'm very curious about the DPU, but that's our next step.
Yeah, well, we'll have Gilad here to talk more about that.
Yeah.
Yeah, go ahead.
So FPGAs, typically we use those for like inference. You need the radiation harden something and put in a space.
Yeah.
Where do you see the use of the FPGAs in conjunction with GPUs? What is the kind of the driving application there?
Okay, very good question. So it is not shown here today. So I'm happy to answer. So our astrophysics code, which is named Argo, consists of the several multi-physics phenomena. So some phenomena is just on the traditional one on the grid space and using the tree code with the gravity calculation. But the other one is a radiation, which crossing all the spaces by the sort of the light arrow. And this computation is relatively short if we make a number of grids, so that it is not good for the vector computation or GPU computation. And also we must compute all the degree, 360 degrees in the 3D space. And it means that there are some of the large number of the random access. So that is not co-accessed with the HBM memory. On the other hand, the FPGA is very tough for even the short vector and also much of the branch conditions with the if then else, because the FPGA has a circuit to run both the then and the else together, so that there is no loss of the computation time. So finally, we found some radiation, space radiation method is more than 15 to 20 times faster than the single GPU on the FPGA. So usually, you know, the FPGA standard flops is much lower than the GPU. But the GPU's flops, it just came from the thousands of the cores in the SIMD manner. So that it requires a very wide, very constant parallel element to be computed. FPGA has almost the opposite side of the direction. And we found that the combination of the two methods, that they are both very important for the final result of the very early universe simulation. And we successfully more than 10 times of the faster computation compared with the GPU-only solution and on the GPU plus FPGA. That is our first and successful application. You can find a couple of papers about that in the, if you're interested in it, I will send you the pointer.
Any remote questions? Yeah. Or you asked? Yeah.
Okay, very nice talk. So my question is on FPGA and the GPU. So is there any study where you are using FPGA and GPU, FPGA, GPU and CPU to do big data analysis or deep learning?
Okay, so the deep learning, FPGA utilization of the deep learning just started in our center. So there is no solution yet. So, but for most of the HPC traditional computation, scenario is very simple. So first we have a performance analysis and make some snapshot. And we found that which part is really bottleneck of the GPU. Then we check the utilization of the GPU cores by the NVIDIA tool. And then think about FPGA implementation of that part. So there always the last 1 mile is a really big problem. And we finally shrink the time for the last 1 mile. That is a radiative transfer computation on the GPU, which makes a big bottleneck. We shrink it about less than 10% of the computation, and so on. So the CPU to GPU, and finally modify some part of the GPU computation into porting FPGA. Of course, this is not a perfect solution. Sometimes we have no solution, even with the coupling. But several classes of the solution problems can be solved in this way.
Okay.
Thank you.
Are there any other questions? Okay, so if not, let's give a thanks.
Thank you very much.
Possibly.